Many people argue that perspective cannot be the reason why the sun is setting and why we perceive the sun the way we perceive it in the sky, that it rises and it dives into the ocean at the horizon when it's setting. And then flat earthers say, of course, it's because of perspective. And other people that believe in the ball earth say it cannot be that, because their argument is that the sun stays the same size throughout the day. And if they argue this way, then first of all you have to tell them the sun actually changes its size a little bit when it goes towards the horizon. When it's coming from the horizon at sunrise, it's bigger than when it is at the zenith. It gets smaller and then it gets bigger again when it goes close to the horizon. But this is caused by refraction, and refraction is happening on both models in reality, okay? Refraction is always happening. Refraction is when objects get magnified by a medium that is between the light source or the object that you're looking at, such as the sun, and your eyes. There is air in between, and when it goes closer to the horizon, you're looking right across the ground of the earth, and so you're looking into this thick layer of air that is very humid on ground level, and so this is causing a magnifying effect. That means the sun at the horizon is getting a little bit bigger because of refraction. That's one aspect. The second thing is that people then argue it cannot be perspective because they look at lamp posts and they say, well, we have that one lamp post and it's so big and huge when it's close to us, but when it goes further away down the street, we almost cannot see the light anymore, or the lamp post itself anymore, because it gets too small to be visible. And they say, look, the lamps, they get so small we cannot even see them, but the sun always stays the same and gets even bigger, the horizon. That's how they argue. So they say perspective cannot be the reason, but let me explain you why it is still the reason. Because you have to understand, when you look at an image or in actual reality, the very first lamppost that you're seeing or that you're even standing under, that light is maybe 2 or 3 meters above you, away from your eyes, and it has that certain size, which comes close to its actual size. And then you look down the line, down the street, at the horizon somewhere, there is this last light that you can spot, and it gets very small. And now you have to understand that the distance you're looking into is maybe 1 kilometer, 2 kilometers, 3 kilometers, when you spot the last light, the last lamppost. So you have 3 meters of distance when the light is close to you, and you have 3 kilometers of distance when you can see the last light. So there is a ratio, right? 3 meters, the lamp that you're seeing that is close to you, 3 kilometers in distance, the lamp that you're spotting at the horizon, the last one that you can see. So there is a huge difference between 3 kilometers and 3 meters. We have to understand geometry and space and ratio and all of this. Because when you look at the sun, at the zenith, it has 6,000 kilometers, according to flat earth calculations. It's not exactly 6,000, it could be between 4 to 6,000 kilometers. That's what you're looking at into distance when you're seeing the sun in the sky. between your eyes and the sun, and you're standing right under because it's at its zenith, okay? And it's almost like the lamppost that you're standing under, but the lamppost was 3 meters of altitude. The sun will be 6,000 kilometers, okay? And I'm just saying this number, don't pin me down on that one, but we have to now realize if the sun is going 6,000 kilometers into one direction, then it's descending because of perspective. That's what it's always doing. But why we always see it in the same size is because when it has gone 6,000 kilometers, we see it dipping into the horizon, we see it going beyond the horizon, but the ratio always stays the same. We're looking 6,000 kilometers up when it's close to us, above our heads, right, in the sky at its zenith, 6,000 kilometers in distance upwards, and then maybe we look 7,000, 8,000 kilometers towards the sun when it's at the horizon. That's why you can almost not see the last lamppost on the street anymore, but you can see the sun always having the same size, and then you put it together with refraction that comes in both cases. Refraction is a thing, whether the earth is a ball or flat, that doesn't matter. By the way, also perspective happens on a ball earth, but ball earthers completely deny perspective somehow. But that is why we always see the sun having a similar size throughout the day, and it's even getting a little bit bigger at the horizon. And you can also tell when there's a day that it's not so humid, that the sun does not get as big at the horizon as it sometimes does, actually, because humidity changes is not the same every day, and so that's why you also get different sizes at different days of the sun. You can take pictures and then you would see that there are slight differences because of humidity in the air. That could all be proven. I don't have the proof here, but that's the theory behind it, okay? And that's correct. So you can apply this, go and make your studies, take pictures, check the humidity at that day, and then you will see that it's linked together, because that is what magnifies objects when you're looking through air that is humid. And why does the sun actually get smaller when it's at its zenith? Because the layer of air that is between you and the sun is much smaller, because we're looking into altitude now, is much smaller than the air, this huge mass of air that is hovering above ground, and you're looking into horizontally, and you're looking through this whole layer of air, plus its humidity in between sun and your eyes. But when the sun is at its zenith, there's this layer of air, and then you have other gases that come on top of that, but the atmosphere is not so high in altitude. You maybe get so you have at least 5,000 kilometers between air and sun that is not air that you're looking through. That's why the sun is not magnified at its zenith, because refraction is almost neglectable in this case, because the layer of air gets very thin on this imaginative line that is between your eyes and the sun. You just have a very small portion of air and then a long portion of some other gases that you're looking through, and these get thinner, and so there is not much magnifying effect going on. But when the sun is at its set, then you're looking through this whole layer of air that is stretched across the whole Earth. Of course you don't see the whole Earth, you see maybe 5 kilometers until there's the horizon, but then there's also still air between, and you're looking through that layer of air that is magnifying things at the horizon.